I'm really delighted to welcome Professor Andrew Cooper to deliver the keynote lecture. Andrew is Professor of Coastal Studies at the School of Geography and Environmental Science in Ulster University. And in 2018, he was identified as one of the top 10 researchers in the world in the field of coastal zone management over the last 40 years. He started his exceptional academic career with a BSc in geology at Queen's University, followed by an MSc and PhD in the University of Natal. His research has included many different environments, investigating geomorphology and sedimentology of estuaries, lagoons, beaches and dunes, and rocky coasts. And he has a wide diversity of research interests, including coastal landforms and morphological behaviour, applying scientific understanding to coastal zone management, especially climate change adaptation, and developing new techniques. He has an outstanding record of research and scholarly activity, with publications in the high 200s and thousands of citations. And is also co-author of The Last Beach with Oren Pilkey, published in 2014. And this is a really important book that sounds the alarm about the future of the world's beaches, and many of the issues which were being discussed just before the session. So it's calling for a change in policy where preservation of beaches is prioritised over property rights. He makes the complexity of coastal systems accessible to a much wider audience, so that people can really be well informed about what's happening. At Ulster University, he teaches undergraduate courses in geography and environmental science programmes, and he's the course director of the postgraduate diploma and MSc in coastal zone management. And in recognition of his outstanding career, he was recently the winner of the Senior Distinguished Research Fellowship Award in Ulster University. So thank you very much, Andrew. We're delighted you can join us.
Thanks very much, Ro. I hope to live up to that introduction. So, yes, I'm going to talk this morning about, well, the title's maybe a little bit dull. In fact, Understanding and Predicting Coastal Change, Geomorphological Perspectives. The real issue is, how do we understand and in the future predict how the coast is going to behave under the various climate change scenarios that we face at the present time. So the background to a lot of our work in geomorphology is global climate change, and at the coast, sea level change is one of the big drivers of our research. We're trying to understand how coasts have responded to sea level rise in the past, and using that information predict how they might behave in the future. So the context to all of this is that sea level is rising globally. The tide gauge data that we have going back to the beginning of the last century seems to suggest an acceleration in the rate of sea level rise. We can see a little bit over 0.5 millimetre up to 1930, then increasing to over 1 millimetre per year up to the 1990s. And with the advent of radar altimetry measurements, we see even more acceleration, up to 3 and possibly 4 millimetres per year in the last few decades. Now, where we head in the future involves a good deal of guesswork, and not uninformed guesswork, but educated guesswork. And we're guided by these various emission scenarios. And using those scenarios, various predictions of future sea level have been made. They range from somewhere around 25 centimetres up to about 1 metre by 2100. There are higher scenarios being talked about, and those depend very much on the rate of ice melt and how much external water is added to the global ocean. And some of those talk about perhaps 2 metres sea level rise by 2100, which really would be a very big increase. Experience now has shown us over the past 2 cycles of the IPCC that reality has tracked the worst case scenario. If that continues to be the case, and it does seem following the Glasgow meeting that it will continue to be the case, we are looking at the high end of these scenarios for sea level change. Associated with that is what will happen at the coast. And to understand that, we've got to think not on the time scale of days or years or seasons, but we've got to think of multi-decadal coastal change. These sea level rise predictions are multi-decadal predictions. And we've got to try and understand the coast at those timescales. And that is a challenge, because what we find out at shorter timescales is not always related to what transpires in the longer timescale. And we have different ways of approaching this. We can look back into the geological record. With the advent of AMS dating, we're able to track geomorphic changes at decadal scales back in the geological record. We have historical records, maps, air photos, anecdotal historical accounts that point us in the direction of how coasts have behaved in the past. And there are modelling approaches of various types. So if one was living or owned a property in a place like Benidorm, this becomes quite an important issue. What is the coastline going to look like in the future? Notwithstanding what humans might do to that coastline, that's very much a nourished beach that we're looking at Benidorm. But the challenge is, will continued beach nourishment be sufficient to hold the shoreline in place for these various sea level rise scenarios? With a sea level rise of 1 or 2 meters, that's a big question. It will require enormous volumes of sand. And if that is to be repeated around all the nourished beaches of the world and the beaches that are not yet nourished, it's going to require an enormous expenditure of money, new sources of sand, and an enormous increase in the engineering capacity to hold the shoreline in place through things like beach nourishment. However, we do know that shorelines change. This photograph from Ocean Isle Beach in North Carolina shows a number of roads that don't appear to go anywhere. Those that are coming out of the screen towards us seem to come to dead ends, and those kind of orange colours around them are sandbags that have been put in place to act as temporary protection for the properties that are threatened by this coastal change. These are temporary measures because in North Carolina there's a ban on hard sea defences, and the sandbags themselves are seen as a stopgap in the hope and expectation that the coast will repair itself. Unfortunately, that seldom happens because the coastline as a whole tends to be moving landwards. However, you can see from that kind of image the importance of having some idea of where the coastline might be in the future. So I come from a geological background, and geologists create what are called FASES models to help them understand what's preserved in the geological record. And we do this in order to distill away the local variability and to generate generic or conceptual models of coastal environments. And geomorphologists do very much the same sort of thing, but for different purposes. It's to try and develop generic understanding of how various systems work. So I want just in the next few slides to look at a few barrier-lagoon systems, just to show the variability amongst them, and then to draw together the generic model that's been created and which is well established now for barrier lagoon systems. So I begin with one in the central coast of Mozambique. It's the Bazaruto archipelago, and it consists of 3 vegetated islands of various sizes. The largest one in the north is the Bazaruto archipelago, or Bazaruto Island. It's fronted by these mobile sand dunes, which are not insignificant features. They're about 30 meters high. Then there's a smaller island to the south and an even smaller one south of that. But this is a easily identifiable barrier island chain separated by tidal inlets, and associated with those tidal inlets are ebb deltas on the seaward side and flood deltas on the landward side. If we go across the Atlantic to the very well-studied barrier lagoons of the eastern United States and take a look at Galveston Island in Texas, it's strongly contrasting, but in some ways similar to the Bazaruto example. Here we have very long and low barrier islands with lots of washover fans, so they're not topped by dunes. Those dunes on Bazaruto prevent overwash from taking place. Between the barrier islands are small tidal inlets with well-developed flood tide deltas and less well-developed ebb tide deltas. Let us come a little nearer to home to the Frisian Islands of the Netherlands, and here we have a chain of barriers of some quite extensive development. They are topped by dunes of varying heights. A lot of them have these areas of bare sand around their tidal inlets, and these reflect the enclosure and reclamation of the polders in the Wadden Sea and in the Zuider Zee. Those have had the effect of reducing the tidal prism, and the tidal prism of lagoons is very much related to the size of the tidal inlets and to the delta systems. So by reclaiming these areas, the Dutch have reduced the amount of water flowing in and out of the Wadden Sea. Consequently, the inlets have shrunk, and they've accumulated this extra sand in the areas where the inlets once were, and that sand has been drawn in from the ebb delta and the flood deltas. Here, even closer to home, is my local barrier lagoon system. That's Loch Foyle. It doesn't look very much like the others, but it does share a number of common characteristics. The barrier is McGilligan foreland. It has a tidal inlet, it has a flood tide delta, and it has an ebb tide delta known as the Tons Bank. It was the site of an abortive scheme to put tidal turbines, sorry, not wind turbines in the ocean several years ago. Although this looks different from the other barrier lagoon systems that I've illustrated, it is nonetheless an identifiable and recognizable barrier lagoon system. Part of the major difference is that its barrier, which this is McGilligan foreland, consists of a series of prograded beach ridges. So this barrier has been advancing seaward as a result of a very large sediment supply during the Holocene. So we can combine all of these components to develop a generic model to which these diverse examples of barrier lagoon systems adhere. There are commonalities, not all of them developed in every barrier lagoon system, but this kind of barrier lagoon model, which has been around since the 1980s, does quite a good job of describing how barrier lagoon systems work. What it doesn't include, however, is the role of any geological parameter. And if we had this barrier lagoon system developed on a rocky coastline as opposed to a coastal plain where there are nothing but erodible and soft sediments, we would see significant differences between the rocky coast model and the coastal plain model. So here I've just highlighted some of the differences that occur whenever we introduce a geological control. On the lower diagram, we see the bedrock influence on the barrier lagoon system. We can see in the upper part of this lower diagram the development of swash-aligned coastal segments. Here between two rocky outcrops we have an embayed beach. Underneath this barrier lagoon system in the south, we have a bedrock pinnacle on which the barrier itself is pinned, and that influences the migration rate of the barrier. On top of this barrier, we've portrayed higher dunes, and those preclude overwash and prevent the landward transfer of sediment across that system, and it makes it behave in quite a different way to the lower part of the barrier, where waves can periodically overtop the dunes and deposit material in the back barrier. I put that up simply to illustrate that there are very easily comprehensible geological influences in how these systems work. And very often we overlook these whenever we think about multi-decadal scale coastal behaviour. So this is a slide given to me by a colleague from Copenhagen. He gave one of the most impressive talks I've heard in quite some time at a conference. And it was the most elegant talk because he presented a series of observations of the coastal change in Denmark over several decades. And he went on to solve this equation for that stretch of coast and was able to prove that the coastline had behaved according to that equation. And I thought it was such an elegant presentation because he set out this proposition and then demonstrated, and almost as if you were in a school maths class, finished off with the letters QED across the top of the screen. Well, this equation is one that includes three components. There's firstly the sea level rise component, known as the Bruin rule, which is illustrated in this diagram below. Then there's a longshore component, which is to do with the movement of sediment along the shore under oblique wave action. And then there's the cross-shore component, which is the exchange of sediment in a shore normal direction from the dunes through the intertidal and subtidal parts of the beach. Critical to that sediment budget equation is this Bruin rule, which is illustrated in the diagram below. And the Bruin rule really says as sea level rises, the profile is maintained. So the profile before sea level rise is the same as that after sea level rise, and the sediment that's eroded from the coast is deposited on the shore face to maintain that profile. Well, I was so impressed with this talk, I asked him for a copy of the presentation, which he happily gave me. And I went away and thought about it a bit. And shortly thereafter, I was at a meeting in New Jersey, the Binghamton Symposium on Geomorphology, which happened to focus on coastal geomorphology in that year. And there were two talks, which I'll come back to a little later. One talking about the response of coastal dunes to storms and how the morphology of those dunes was really crucial in describing how the dunes behaved. And the second was a talk by Edward Anthony, where he talked about the linkages between nearshore sandbars, intertidal beaches, and dunes in the southern North Sea. Both of those talks made the incontestable point that the geomorphology and the geology were critical components of how those coasts behaved at multi-decadal timescales. And that got me questioning the presentation which I'd heard from our Danish colleague. Now, we know simply by a process of thinking about it, but it can be demonstrated from the literature, that there are really important geological constraints on how barrier lagoons behave. The geological framework I've already alluded to. There are often geological pinning points. There are geological outcrops that prevent erosion. There are sometimes geological outcrops that can be eroded and supply sediment, but there are nonetheless important and I think incontestable contributions from the geological framework in how a barrier lagoon coast works. Another important parameter is the volume of barrier sediment. I've already mentioned that some barriers can be overwashed and others are not overwashed simply as a result of the presence or absence of dunes, and we'll come back to that later. But that strongly influences how a barrier system in particular operates. Then the question of sediment supply, the rate of sediment supply, where the sediment's coming from, and how it's delivered to the coast are very clearly important constraints on how a barrier lagoon system works. Then importantly, not just the amount of sea level rise, but the rate of sea level rise and the previous sea level history are important constraints on how a barrier lagoon changes. We'll see from some examples I'll show later, there are times when the rate of sea level rise is so high that the coastline is simply flooded and stranded on the shore face. There are other times when the coastline retreats steadily and erodes steadily during periods of relatively slow sea level rise. Okay, we also know that storms and extreme events are important in coastal behaviour, and that if we're dealing with multi-decadal timescales, the chances are we're going to encounter some storms or extreme events like tsunamis. However, the impacts of storms, experience is now telling us, is not ubiquitous. We don't always see the same impact of a storm of the same magnitude, same duration. They don't produce the same impact on different coasts, nor do they produce the same impact on the same coast if they occur within a short distance or a short temporal distance of each other. We also see things like the coupling or decoupling of the shore face and the beach. And what we're talking about here is the fact that the shore face operates at long time scales, the beach operates at short time scales. Sometimes things happen on the beach that are not matched by what happens on the shore face. The result of that is that the shape of the nearshore profile changes. And again, I'll come back and demonstrate that in a moment. We also have the question of relaxation times and response times. Again, geomorphological research is showing us increasingly that the impact of very big events very often is followed by decades of post-event recovery. And if we haven't captured the big event, or we haven't got a long enough time scale of our records, we're not picking that up, and we think that's simply the long-term behaviour of the system. And then finally, maybe the most important aspect in understanding multi-decadal coastal behaviour is the process of feedback. We're dealing with coastal systems, and they demonstrate both positive and negative feedback. And increasingly, we're seeing what we might call emergent behaviour, where the link between process and form breaks down, and the coastline is behaving almost independently of the forcing mechanisms. So I want to just investigate a few of those aspects in the next few slides. Let me begin with the geological framework. This is a rather grainy picture, I'm afraid, of some of the islands of the Outer Hebrides in Western Scotland. And on the left part of the picture is the open Atlantic. On the right is the Sound, which is much more low energy. But on the open Atlantic coast, we have these sandy beaches backed by low aeolian deposits, sometimes called macaire. But they constitute essentially barrier lagoon systems. Doesn't look very much like it in that image, but I'll show you some more in a moment. So back in 2012, we were working in that area and concluded that these systems are in fact barrier islands. They're different in some cases from the classical barrier island, barrier lagoon system because of the role of the underlying bedrock geology. But we have argued that they actually exist in a chain of barriers that extends for more than 100 kilometers from the south of South Uist to the north of North Uist. And it's this relatively unbroken chain of barriers and lagoons that constitutes this barrier island chain. Now, some of them are undeniable barrier lagoon systems. Others take a little bit of persuasion, and I'm going to explain why that's the case. In some cases, we have a beach backed by low dunes and fronted by a mobile shore face. In other cases, we have beaches backed by dunes and fronted by bedrock outcrop on which the seaweed has accumulated in this particular picture. We can see the bedrock in the central part of the image, and we can see gravel and boulders overlying the bedrock in this part. So this part of the system has got no shore face. The mobility of the system is confined to the upper intertidal and the supertidal zone. In this stretch, however, we do have a shore face. It extends offshore, and it's because the bedrock geology is low. So in this stretch of the coastline, we have mobility in the subtidal, intertidal, and supertidal. And because we have a bigger accommodation space, we've got a bigger sediment volume, and that's contributed to these much more substantial dunes. That means that in some cases, these barriers are migrating over bedrock, as in this picture. The bedrock is actually quite planar. And in some cases, they're migrating over back barrier sediments. Here we see back barrier peats exposed on the foreshore, and there's the barrier sitting on top of those, illustrating that it's migrating in the landward direction. So we have essentially two types of barrier lagoon systems in the Outer Hebrides. One are very similar to the classical model. They consist of barrier islands, albeit pinned to bedrock, but separated by tidal inlets with ebb deltas and flood deltas, and pretty much unequivocal barrier lagoon inlet systems. These are developed in topographic lows in the bedrock. Where the topography is higher, however, we don't have the space for those systems to accumulate. So instead, we have perched lagoons impounded by the macaire, or low dunes in this case, and fronted by intertidal beaches with or without a shore face. A variation on the same theme, if you like. And we have these two types of systems juxtaposed, the bedrock low systems, the bedrock high systems. We can identify that in the here and now and demonstrate it quite clearly. However, the importance of this for future coastal evolution is really quite important, because as these barriers migrate, they're going to migrate from, in some cases, from topographic low to topographic high, and in some cases from topographic high to topographic low. The consequence of that is that their future morphology depends entirely on the topography of the basement over which they're migrating. So we can demonstrate very clearly here the role of the underlying geology in the coastal behaviour, quite independently of the dynamics. Okay, let me move on then to the volume of sediment in the barrier. And I'm going to contrast two situations here, one where the barriers are small and one where the volume of sediment in the barrier is very big. So this is an oblique satellite image of the central part of Chesapeake Bay. These are barrier islands developed around the margins of the marsh in the Chesapeake Bay. They're affected by waves from both directions, and these little barriers are small but very distinctive barrier lagoon systems. We have termed them fetch limited barriers because of the low energy systems within which they occur. But I'm going to look at it at a time series here of one barrier as it evolves from 1994 through to the early 2000s. So here's an image from Google Earth of a particular barrier in the Chesapeake Bay region. When we look at it in 1994, we see a embayed component in the upper part of the image. It's attached to a marsh headland in this region, and another marsh headland down here. This is an embayed part, and here is a spit part. The spit in that image is starting to break down. We can see that it's breaking down into small parts and beginning to decay. Now here's the same image, or the same location in 2005. So from 1994, we can see that the upper part of the system has retreated. The lower part of the system has had a fresh sediment influx. So instead of the decayed spit, we now see a fresh and elongated spit developed. It's migrating in the landward direction, and it's extending toward the south. We can see a recurve at the bottom that indicates this southward progradation. We skip forward 2 years to 2007. We see it's migrated a little bit further landwards, and it has extended to the south. If we skip forward another 2 years, we see that it's migrating in the landward direction through a process of barrier rollover. So sediment has been transported from the seaward side into the lagoon side, and the barrier is rolling landwards. By 2011, we've come back close to the 1994 situation, The barrier is decayed, it's breaking down, and it's exposing the marsh coastline to direct wave attack from the open parts of the Chesapeake Bay. Similarly, this formerly embayed and smooth planform is breaking down. Sails are beginning to develop along the shoreline, and the sediment supply is clearly broken down. So if we compare those two, the start and finish points, we can see the importance of sediment supply to the behaviour of that system at a multi-decadal timescale. As an influx of sediment restored the spit. The dynamic processes in the absence of more sediment supply caused it to elongate and then roll landwards, and then it broke down in very much the same way that Julian Orford and Bill Carter have described the behaviour of gravel barriers in the open ocean. These seem to be behaving in a very similar way, although they are sand barriers in a fetch-limited environment. If, in complete contrast, we look at a barrier that has a large volume of sediment in it, and here's one on the KwaZulu-Natal coast of South Africa. This barrier is up to 100 meters high. It's topped by a dune forest. It's partly of Pleistocene age, but it's capped and in some cases consists entirely of a Holocene veneer. Those dunes contain so much sediment that they're obviously not ever overwashed, nor have they migrated during the last two glacial cycles. So these have remained in situ, and the coastline has evolved with those in place when sea level has dropped to minus 130 meters and risen as high as plus 6 meters. And those dunes have continued to affect the coastline and the evolution of the associated barrier lagoons during that entire period. That role is down simply to the volume of sediment in the barrier. There's so much material in there, so much inertia to overcome, that it hasn't moved for the last two glacial cycles. Here's another barrier with a high sediment supply in Casino Beach in Brazil. It's fronting the largest lagoon system in the world, the Lagoa dos Patos. It runs for about 200 kilometers in an unbroken stretch along the southern Brazilian coast, and it is supplied by sediment from the continental shelf. It doesn't have the high dunes of the South African examples, but it has a very wide coastal barrier across which overwash is inconceivable, and instead the modern dynamics affect only the seaward edge of that barrier. So in terms of sediment supply, we can see from just a few examples, it's a really important constraint on how coastlines behave at the multi-decadal timescale. And we can have sediment supply from a variety of sources. It can come from the continental shelf. It can be supplied by contemporary rivers or by former rivers during sea level low stands. It can be supplied by shoreline erosion in the updrift direction from the coast in question. Or there are places where there is no contemporary sediment supply. A lot of the paraglacial coasts of the world, for example, have a very low contemporary sediment supply. And we can say with certainty that sediment supply is a very important constraint on multi-decadal coastline behaviour. It is, however, very difficult to quantify and difficult to take account of other than in a qualitative way when we try to understand coastal behaviour. Okay, let me move on to talk a little bit about the rate of sea level rise. Okay, a lot of our predictions talk about where sea level might be by 2100, but that involves a rate of sea level rise, and we know it's been our sea level rise has been accelerating over the last century or so, but the rate at which sea level rises, we know from geological investigations, is very important for how the coastline responds. It's not just the amount. And I want to illustrate that by some work that we've done on the South African shelf, where we have a combination of multi-beam bathymetry and seismic profiling that has allowed us to reveal on the seabed these submerged barrier lagoon systems. Now that coloured part of the image is the multi-beam bathymetry. The bluer shades are deeper water, the red shades are shallower water. And in the little square, you can see the outline of a sort of almost circular feature on the seabed. It's impounded by this linear dark green coloured feature, which is a submerged barrier. And that's sitting at about 60 metres water depth. And in behind that barrier is, in the blow up, you can see it there, remnant of the lagoon with a cuspate spit that has developed inside the lagoon. And that is identical in form to the lagoons that we see on the contemporary KwaZulu-Natal coast that's illustrated by the little inset from Google Earth. So what we have on the Durban Shelf is a series of submerged barrier shorelines that are almost wholly preserved. Even the individual components of that cuspate spit are preserved on the seabed. We find two distinctive shorelines, and this is ubiquitous around the southern African coast and on the Brazilian coast, that are developed at minus 60 metres and minus 100 metres. Those turn out to be times when sea level was relatively stable, and they were periods immediately before there was a period of rapid sea level rise. The minus 60 metre shoreline in particular is backed landwards by several segmented lagoonal water bodies, and those have been preserved on the seabed. Now, if the Bruin rule was operating during these times, these would not be preserved. The Bruin rule says that the coastline is eroded as sea level rises, and the sediment that's eroded from the coastline is deposited on the shelf. That doesn't allow for the preservation of shorelines like this. So we know with absolute certainty the Bruin rule is not a ubiquitous description of how coastlines behave in response to sea level rise. Now, those periods of, or those shorelines at minus 60 and minus 100 metres coincide with, as I've said, with periods of relatively slow sea level change. Those are periods when the sea level was stable and it allowed the development of complex shoreline morphologies. But they were succeeded in both cases by periods of very rapid sea level rise, one of which is meltwater pulse 1A, and the second is meltwater pulse 1B. During these times, sea level rose at very high rates. So in meltwater pulse 1A, between 14.6 and 13.8 thousand years ago, sea level rose 16 metres at 2 centimetres per year. Okay, at the moment, we're talking about 4 millimetres per year. And during meltwater pulse 1B, it was even faster. In 300 years, sea level rose by 18 metres, and that equates to 6 centimetres per year. So these were very fast rates of sea level rise. And that makes sense, because if we're to preserve something on the seabed where we have high wave action, we've got to get those waves over that coastal sediment body very quickly if it's to be preserved and not eroded. Okay, let me turn now for a moment or two to the role of storms or extreme events. This is a photograph of before and after of the impacts of Hurricane Sandy. It comes from the USGS website. And we see in the top picture a continuous barrier in the pre-Sandy situation. The little yellow arrow is pointing out a place that's located in the lower picture as well. In the post-Sandy photograph, there's the same little yellow arrow, and we can see the barrier has been broken, a new tidal inlet is forming. Now, if you look up at the upper picture again, you do see a sand body in the middle part of the lagoon. That sand body is a remnant of a former flood tide delta. So it tells us that this barrier had breached in this location before, and it breached once again during Hurricane Sandy. It wasn't allowed to remain open, it was closed because that's what the US Army Corps of Engineers does these days. It closes up inlets that are formed in the barrier lagoon systems. But this formation of inlets is a key component of storm impacts. If the inlet is formed and it persists, it changes the morphology of the coast in its vicinity. it develops new flood tide deltas and new ebb tide deltas, and to do so, it draws in sediment from the surrounding coast. And it creates a point source, if you like, or a point at which really dramatic changes take place at the coastline as a result of a single event, or in this case, perhaps as a result of recurring events in the same location. So we know, again, from observations that storms are important determinants of coastal behaviour, not just in this kind of environment, but even in our own environment. The work that Melanie has been talking about earlier in Dundrum Bay shows very clearly the importance of storms in changing the morphology of intertidal sandbars in Dundrum Bay. Now, sometimes in the historical record, we come across really extreme events. One of those was the 1634 North Sea storm. Okay, beside it, the 1953 storm surge, which is perhaps the best known because of its impacts on both sides of the North Sea. Besides this one, it pales into insignificance. 15,000 people died in the 1634 storm. That's a woodcut depicting its impacts on the German North Sea coast. And quite recently, some work done by our Danish colleagues discovered that as a result of that storm, the coastline was displaced seaward by between 3 and 4 kilometres compared to the pre-storm situation. Okay, in this case, this is displaced seaward, not landwards. The impact of this storm was to reach deeper into the sediments on the North Sea, push those sediments landwards, and create a new chain of barrier islands that weren't there before. And the Furgaard and his colleagues have demonstrated quite clearly from both cartographic evidence and from geological evidence that this chain of barrier islands formed as a result of that storm. And you can see the succession of events on the right. We begin in the pre-storm period, 1612, in the upper diagram. By 1650, after the storm had happened, we've got a big aggradational shoal, and that shoal gradually moved in a landwards direction and formed, first of all, the Scalligan Spit, and subsequently these barrier islands that are now well-developed features on the North Sea coast. So storms can have both erosive impacts and they can have depositional impacts. Okay, I want to turn now to the linkages between the barrier and what happens on the seaward side, because we know that barriers are intrinsically linked to their seaward extension. It's very clear on beaches, for example. Beaches exchange sediment with the near shore. We see that very clearly in the kind of winter-summer transition, where sediments eroded from a reflective beach during the winter time. The beach becomes dissipative. Sediment accumulates offshore and builds sandbars, creating a dissipative profile. And in the summertime, the sand is pushed back onshore, creating a reflective profile. So there's a clear exchange of sediment that we can see on a seasonal basis. Well, this also exists at multi-decadal timescales, and sediment is exchanged between the near shore and the shore face. And our observations from various locations show that that is not always done in the same way or following the same pattern. So I compiled several examples of how this happens from the literature. In the upper diagram, we see in the red dashed lines 2 former locations of the nearshore profile, and the annotation T1, T2, and T3 are successive times as sea level is rising across the shoreline. So at T1, the line is depicting sea level at that time. The dashed line associated with it shows the nearshore profile. Right, let's go here. The nearshore profile coming down to perhaps the depth of closure. And as sea level rises, that profile is being maintained in this diagram. And under these circumstances, the rate of shore face retreat is equivalent to the rate of shoreline retreat. And there's been good observations of that from the Louisiana coast. In the next diagram, we have a situation where the rate of shore-face retreat is slower than the rate of shoreline retreat. We know that to be true intuitively, but there are many observations of it in practice. The North Carolina coast is a good example. The shore face has not been retreating as fast as the shoreline. That's because waves reach the shore face much less frequently. So consequently, the shape of the cross-shore profile has been changing. It's becoming wider and flatter as time goes on. Now, where that leads us gives rise to two possibilities. In the one case, in the lower part of the diagram toward the left, the shoreline can excavate a new shore face, and that's happening on the Frisian Islands at the present time. Or on the right-hand side of this diagram, we see that the shoreline stabilizes, sediment moves landward from the shore face to the coast, and gradually the shoreline stabilizes and the shore face catches up. And that's exactly what's happening on the mainland Dutch coast at the present time. So I began by talking about the fact that I couldn't match the elegant equation that described the Danish coastal behaviour with what I'd seen at the Binghamton Symposium. And I want to just say a brief thing about each of these two papers that I referred to earlier, one by Chris Hauser and the other by Edward Anthony. They both make the very strong point about feedback. And Hauser shows in terms of how storms affected dune coast, that the impact of an extreme storm is sensitive to the initial conditions, and specifically the pre-storm variability of the dune crest elevation. Okay, and he concludes that this in turn suggests the evolution of barrier islands depends on the storm history until the variability in the dune line elevation reaches a maximum. So a very clear feedback demonstrated by observations of multi-decadal coastal change on that Gulf of Mexico coast. Similarly, Edward Anthony showed in the French Channel coast that the sandbanks, the intertidal sandbanks, evolve under the joint control of tide, wave, and wind-induced currents, which stretch them out, so the geomorphology changes. That leads to bank division, where they break up, then shoaling and breaking wave storms, which drive them onshore. So he concludes the banks modulate the delivery of storm wave energy to the coast. They redirect the currents along the shore and are the sand sources for the accretion of coastal dunes. This is far from a straightforward exchange of sediment between the near shore and the onshore. And one of the nicest illustrations of feedback involves the relationship between the tidal prism and the size of the tidal inlet and the associated ebb delta. And it's demonstrated very nicely in this conceptual model from Duncan Fitzgerald. Here in the top left is the initial stage of a relationship between the tidal prism and the ebb tide delta. The linear relationship is shown by this dashed line. So at the initial stage, there's a balance between a relatively small tidal prism and a relatively small ebb tide delta. Okay, as sea level rises in the top right, we move to a situation where the tidal prism increases and the ebb delta volume increases accordingly. The sediment to do that comes from the barriers themselves, so the barriers shrink. Okay, when we move down to stage 2, the tidal prism has got even bigger, the ebb deltas have got even bigger, the barrier islands have become smaller, and at stage 3, the barrier islands have almost broken down because they're unable to sustain the size of the ebb delta that the tidal prism demands. And Fitzgerald refers to this as runaway transgression. And it calls it a runaway transgression because at that instant, the open ocean waves shift from the barrier system to the near shore, to the back side of the lagoon. Okay, in the Outer Banks of North Carolina, that would involve a 50-kilometer shift in the littoral zone, which might happen overnight as the barrier islands break down. The point is that there's an important feedback here that complicates how the coast works at multi-decadal timescales. So here's where we started. We had the sediment budget equation that was solved for the Danish Barrier Island coast. And as I said, it was very elegant. It produced a very clear agreement between the data and the equation. Does it make sense and can it be applied elsewhere? Well, I think not. Rather than writing QED, we have to put a big line through that and say that coasts are much more complex than that. They can't be described by simple equations. And there is a very strong geomorphological and very strong geological control on how they behave. So where does that leave us? It sounds maybe a rather bleak situation. And there are several issues in predicting and understanding barrier lagoon behaviour. I think a lot of those centre around a fixation on dynamics and an inability to quantify, let alone recognise these other geological controls. The idea of a unifying model like the Bruin rule or like the Steva equation is very appealing. It would be very nice to be able to apply a unified model to a global data set, such as been done recently by some global scale investigations. But it would be entirely untrue to do so, and it would be entirely misguided to do so. We have the question of, do the archetypical systems that we create for geological and geomorphological purposes actually exist in nature? And how important are the exceptions and the local variability in determining coastal behaviour? I think this is perhaps the crux of the matter. The conceptual model for barrier lagoons, for example, is very useful for us understanding in broad terms how these systems work. But when we're to describe a given system, the noise or the local variability turns out to be much more important on controlling the multi-decadal behaviour than the generic exchanges that take place within that system. And if we are to understand and quantify those generic exchanges, we need much more information on the local situation to properly predict where the coast is going in the future. Now, a couple of years ago, I had too much time in my hands and I sat down to read War and Peace. It took me all summer to do it. It's quite an engaging read, I must say, and it spoke to me in some ways about geomorphology. One of Tolstoy's findings with regard to history was that history is not made by generals making decisions that dictate the outcome of battles and wars. He argues that great events are the result of many smaller events driven by the thousands of individuals involved. So an individual soldier will make a decision that influences the way his compatriots and therefore the whole regiment and therefore the whole army behave. He argues that these smaller events are the result of necessity and free will, these two components. Necessity being based on reason and therefore explainable, and free will being based on consciousness and therefore inherently unpredictable. Well, I think coasts are maybe a little bit like that. They behave according to the laws of physics, by all means they do. However, they behave in that way within a given geological and geomorphic context. The importance of the geomorphic and geological components cannot be overstated, and they present a challenge for us to understand the past behaviour, let alone the future behaviour of coastlines. But this is a little summary diagram to kind of show how some of these factors influence the behaviour of coastal geomorphic systems. So the coastal orientation determines very much whether we've got an equilibrium plan form or drift or swash alignment. The basement characteristics influence the slope, the irregularity, the erodibility of the barrier, and they in turn influence the barrier's orientation, lagoon's orientation and dimensions. They influence the shore face morphology. Sediment supply influences the volume of sediment in the barrier, whether there is a shore face or not. They influence the grain size, the barrier elevation, and so on. And all of these factors combine to produce influences on coastal behaviour that we need to take account of whenever we're trying to understand it. From evolutionary biology, Stephen Jay Gould concluded that so many chance events were involved in the evolution of life on Earth that if we were to rerun the evolutionary clock, we wouldn't produce the same result. There are so many chance juxtapositions of events that we wouldn't come up with the same thing if we ran time all over again. And so it may be with coasts. The chance juxtaposition of a storm with the timing of a previous storm, or with the migration along shore of a large body of sand, or with another fortuitous event, lead to the juxtaposition of events and morphology in time and space that it makes it very difficult, if not impossible, to predict. So to conclude, I put up this little diagram just to illustrate the importance of geological and geomorphic factors. If we view the coast as a system, we have a variety of inputs, so storms, sea level change, the cumulative effect of microscale processes, and sediment supply. These serve as inputs to our coastal system. The coastal system itself is influenced by various geological parameters that influence its contemporary geomorphology. Its morphology at time zero. And those in combination with the inputs determine the barrier response. They determine whether a barrier rolls over, is overstepped, erodes, breaks down, becomes longer, whether inlets open and close, whether the barrier aggrades or progrades. There are a diversity of controls on the barrier response, and the barrier response is reflected in its multi-decadal behaviour. So this, I think, is our challenge, to understand these relationships better, to document more and more examples, and perhaps out of these we may be able to draw some generic conclusions. But at the moment, our generic models are not up to the task. So I'll finish off there.